Hello again, everyone. Again, I'm really missing you, and I hope you're doing well. So we're going to start the last section of Chapter 9 today, so 9.4, and that is looking at some more geometric series, but these ones are infinite, so meaning that they don't end, they keep going on forever. There's not a specific number of terms. So you can still find the sum of a geometric sequence that has an infinite number of terms. The formula is a little bit different though. You just do the sum equals the first term divided by 1 minus the common ratio. So up above you can see the one that we were using before. This one is a little bit more simple compared to this one. So we'll get some examples where we do this, and then we'll also look at whether the series converges or diverges. So converges means that it gets closer and closer to a particular sum. So it would get closer and closer to this sum here. And that is the case when your absolute value of your common ratio is less than 1. So if it's anywhere between 0 to 0.99999, right? So not equal to 1, but as less than 1. And then it's diverges, meaning it does not approach a particular sum if the common ratio, the absolute value of it, is greater than or equal to 1. So 1 and up. So let's go ahead and jump into some examples and practice these. Okay, so here's the first example. We're going to look at this geometric series and we're going to determine if it diverges and converges, and then if it has a sum or not. So remember that to determine if it converges or diverges is we're looking at the absolute value of r. And if it's less than 1, then it converges. And then if it is greater than or equal to 1, it's going to diverge. So let's go ahead and take a look. Let's find the common ratio. You can find the common ratio two ways. So you could find the first two terms, where n equals 1, n equals 2, and then you would plug in 8 times 0.5 to the 1 plus 1 and get that term, and then do the same thing with that one. Or you can just look right here, and that is our ratio. So sometimes you might have to find the ratio by doing the first term and second term. So again, if we had done that, this would have been 2, and then we would have done 8 times 0.5 to the 2 plus 1 and gotten 1. And then we would find what's the pattern there, which is timesing by 0.5. So our common ratio is 0.5. So when we take the absolute value of that, we still get 0.5. So that's less than 1. So since this is less than 1, it is going to converge, which means it also has a sum. So if it converges, it has a sum. Diverges, it doesn't have a sum. So it converges and has a sum. Okay, so let's go ahead and do some try-it problems now. Switch to that screen. So here are your try-it problems. Determine if it converges or diverges, and then if it has a sum or not. So go ahead and pause the video and give it a try. Okay, so hopefully you gave those a try, and then you have to find the common ratio, which was 1.2. The absolute value of 1.2 is still 1.2. Since this is bigger than 1, it's going to diverge, so it does not have a sum. And then over here, you can go ahead and find the common ratio here. Take the absolute value of -3, and you get 3. So again, bigger than 1. So it's going to diverge and not have a sum. If you have any questions about this, please email Miss Holstad and we will get back to you. We have a couple more examples that we're going to take a look at, so let me change the screen to those. Okay, so now we have a word problem. So a pendulum travels through an arc of 48 feet on the first swing. With each successive swing, the pendulum travels 99% of the distance traveled on the previous swing. Excuse me. Model the total distance traveled by the pendulum with an infinite geometric series and calculate how far the pendulum will swing before coming to a stop. So we are going to be looking at a few things. So let's highlight the key information. So it says the first swing is 48 feet. So that is going to be my A1, my first term. And then with each successive swing, it's going to go 99%. So I'm going to change that to a decimal, but that is going to be my common ratio. And then it wants to model the total distance. So total distance would be the sum. So we're calculating how far it swings. So the total distance moved. So remember, to find the sum, we use S equals the first term divided by 1 minus the common ratio. So, we said the common ratio is that 0.99, but we need to change it to 99% to a decimal, so 0.99. So that's what's going to go there. And then we have our A1, which is the 48 feet. So plug it in. 48 divide by 1 minus 0.99. So then put that into your calculator and you're going to get 4,800. So our final answer is the pendulum moves a total of 4,800 feet. Okay, so there's that one. Again, if you have any questions, email Miss Holstad and we will be happy to help you. We wish we could help you in person, but we will make do with what we have. Okay, so go ahead and give this one a try. So make sure to pause the video and then give it a try and then check your work with mine. Okay, so checking your work again, we need the first term, so we plug in n equals 1 to here and then solve it and we get 0.08. So that's what I'm going to plug in here. And then our ratio you can find here, or you can do the math of the first term and the second term and find that ratio. And that's going to go there. And then you go ahead and plug it into your calculator. Again, if you did 0.1 instead of 1 over 10, that is completely fine. It's the same thing. So then you get a final answer of the sum equals 0.08 repeated. Okay, so I have an activity that I want you to go ahead and give a try. So I'm going to switch to that screen. Okay, so at first you're like, whoa, that's a lot of writing, right? So let's just break it down. We're looking at a fractal, which is a geometric figure created through recursive procedure. So basically, we're just going to look at one example of a fractal. There are many different fractal examples, but we're going to look at this one here, where in the first step it just starts with an equilateral triangle. So don't mind my drawing. I tried my best on this tablet, but if you want to see it, I can upload a picture of it later on, or you can just search this right here and you'll find it. Okay, so it starts with an equilateral triangle, and then each step will add a series of 4 segments. So it adds the red ones here, and the red one there. And then the next step, the black is that old red one right here, and it adds another 2 triangles on each side. And then in the next step, again, the black is all these one now, and then the red is the new again. I know it's pretty messy, and I apologize. I tried my very best on this tablet, so don't judge my drawing, please. So what we're going to do with this fractal is we're going to actually look at the perimeter and the area of it. So below, I have written the perimeter and the area in terms of geometric series. So you have the perimeter here, and then the area here. And you're going to go ahead and just answer a series of questions based on using these 2 sigma notations for the area and the perimeter. So go ahead and pause the video, give those a try. Again, this is kind of like an activity kind of challenge a little bit, the thinking, and apply it to something in the world. So pause it, try your very best, and then check your answers. Okay, so hopefully you paused it and you gave it a try. So the first one is, what is the common ratio for the perimeter? Well, let's look at it. Here is our common ratio for the perimeter. And then here would be our common ratio for the area. So for the perimeter, it is 4/3. For the area, it is 4/9. Then it asks, does it converge or diverge? So looking at the perimeter, our ratio is 4/3. Take the absolute value of that, and we get 4/3. That is greater than 1. So it is going to diverge. Does the area converge or diverge? We're looking at 4/9, which is 4/9. That is less than 1. So it's going to converge. And then it says, describe the relationship between the area and the perimeter. So the area converges, which means it does have a sum. Whereas the perimeter diverges, so it does not have a sum. Okay, so that is it for today. Again, if you have any suggestions or comments, questions, we are here for you. And even though we're not there in person, we are here to support you as much as we can. So please do not feel like you email us too much or anything like that. We are here for you. Hope you all are doing well. Thanks. Bye.